I'm going to talk a little bit about temperature measurement devices. Now, there are all sorts of old school temperature measurement devices that don't work out so well when we try to incorporate them into modern microcontroller based systems. For example, liquid and glass thermometers. You really need somebody there to watch them. Bimetal strips bonded here, which have differential expansion, allow you to create some physical motion in a sensor, which if you had an analog system like this thermostat would allow you to flick a bulb full of mercury back and forth to make and break electrical contacts with a bubble of mercury. Now, why wouldn't we want mercury in our control systems now? Well, for a start, this analog control is a little difficult to manage and interface with the rest of our systems. And for another, mercury is toxic. So let's move on to something a little more modern. Analog IC sensors like the TMP36 you've been working with rely on the temperature sensitivity of integrated circuit components. And in this particular case, it's the difference in size of these transistors that causes them to perform a little bit differently with changes in temperature. There's additional circuitry in here to linearize that and give us a predictable output result. So as mechanical engineers, we don't really need to know exactly what's going on inside the transducer if we go to the data sheet and find out what's going on the outside of the transducer. And the data sheet will tell us how to make our connections. It'll tell us the scale factor, 10 millivolts per degree Celsius, something about the accuracy and linearity of these transducers, and what kind of voltages we need to operate them with. So data sheets provide a wealth of information about how these transducers will actually function in your measurement system. TMP36, about $1.50 in quantity one. So these are pretty cheap sensors. From the data sheet, we find, for example, this line B for the TMP36 shows that at 0 degrees C, we expect to get 1/2 volt. At 50 degrees C, we expect to get 1 volt. And at 100 degrees C, we expect to get 1.5 volts. And that we expect a linear change in voltage on the output of that TMP36 as we go along. This thermal response graph tells us about how quickly our TMP36 can be expected to respond when mounted in a variety of different ways. So generally, these things are fairly slow. It's going to take tens or hundreds of seconds to get a good response out of them. This gives some indications about the accuracy levels. Typically, they say it's really good, but maximum limits, positive and negative, go out to plus or minus about 3 degrees Celsius. So that plus or minus 2 degrees as an uncertainty is not taking it out to the maximum, but is still probably a good number to use as a 95% uncertainty, plus or minus 2 standard deviations. One of the disadvantages with something like one of these analog TMP36s is that we're still dealing with an analog signal. We're getting a millivolt output that we've got to interpret. If we took the same sorts of capabilities in the circuitry and added a little computational ability on a slightly newer device, we could communicate digitally direct with our microcontroller, and we might be able to get more accuracy. We've still got the same sort of size of package here, so it's still going to be slow to respond, but often that's not really a problem. This MCP 9808 costs about $1 in quantity one. It's small. We can see the measured typical distribution of accuracy over 854 units, it says here. So I'm ready to believe in that plus or minus 0.25 accuracy that they're claiming up here. So much more accurate than the TMP36. Now, if we want to go faster, or we want to get to be really, really accurate, we may need to go back to analog temperature transducers. And they're going to rely on changes in resistance or voltage and probably require additional electric circuits to get our signal so that we can read it with our microcontrollers. And one of the problems with using analog temperature transducers is that changes in other conditions, for example, strain, can also change the resistance or the voltage or whatever it is that we're trying to measure in an analog way. Also, wherever we've got analog signals, we're going to be subject to electrical noise, and the longer that cable runs carrying that analog signal, the more electrical noise we're going to have induced by the radio frequency noise that's present in just about every engineering environment. So examples of materials that you can use in resistance sensors, there are a whole lot of fairly exotic materials. One that stands out for high precision and high quality temperature measurements is platinum. It can be used in resistance temperature detectors, and although platinum has a very low resistance at very low temperatures, in the realistic engineering range for most applications, it's got a resistance that varies almost linearly, and platinum has the advantage of being well behaved, able to take high temperatures, stable, non-corroding. Platinum has a lot of pluses. The downside, platinum is expensive. If we're looking for something cheaper in a resistance temperature detector, we can go to thermistors. Thermistors are solid state devices, and they have non-linear variations in their resistance. However, if you put them into a circuit, you can use something as simple as a voltage divider to be able to interpret them and figure out what the temperature is in a particular circuit. The type of sensor that you're most likely to encounter in an industrial environment is some kind of a sealed metal temperature sensor like these. These metal sheaths protect the sensor from whatever environment you're putting it into, and these particular ones have platinum resistance detectors inside these capsules. Now, to give you an idea of what's going on inside the capsule, an evacuated space will keep the platinum from interacting electrically with the sheath out here, and will allow us to keep the platinum and anything else that's in there from corroding or otherwise being sensitive to anything other than the temperature of this exterior sheath. This platinum wire is wrapped carefully on a non-conducting support so that it's not going to be, and it's coiled like this, so that it's not going to be subject to strain, which would also change the resistance. And then finally, the relative resistance, the change in the resistance of that platinum resistor will go up substantially over a wide range of temperature. And if we're trying to do precision measurements over a smaller range of temperature, we can get very accurate results by measuring very small changes in resistance with the Wheatstone bridge. Very commonly used transducers are thermocouples. Big plus on thermocouples, they're pretty cheap and they're very rugged. Now, the way a basic thermocouple circuit works is if we're trying to measure what's going on out here at in this sample at temperature T1, then if we have two dissimilar metallic materials, material A and material B, put together into a circuit like this, if these two temperatures are different, then the potential across that junction between dissimilar metals will be different at each end here because it's a function of temperature. And the result is that the difference voltage V0 will show up here, and that'll be related to the difference in temperature between T1 and T2. Now, we're going to have to be a little more sophisticated when we do that. You've already tried this in the labs, and you saw that when these two temperatures were about the same, you got 0 volts here, and then you got an increasing voltage as you increase the temperature of one junction relative to the other. To do a proper job here, we need to do what's called cold junction compensation. And traditionally what you did was you stuck one of those junctions in an ice bath. But it's more likely now what you would do is you would have this junction on your data acquisition system or on your microcontroller and have another slower temperature transducer there to tell you what is the cold junction temperature at your data acquisition system or microcontroller. So we've got a measuring junction, we've got a reference junction. Or if we want to, we can have two reference junctions out here to bring both these more exotic metals back to being copper on their way back to the voltmeter. Either one winds up electrically equivalent. And what we'll see at the meter depends on the forward voltage across the measurement junction minus the reverse voltage across the reference junction. Or to put it another way, if what we really wanted to know was what was the voltage across the measuring junction, we could take whatever we measured at the meter and we could add on whatever voltage we knew for the reference junction. And then we can go into the tables or use a curve fit to get the corresponding temperature. That can get pretty involved because thermocouple materials, different thermocouple materials, have different relationships between the voltage and the temperature. And in addition to having relationships that are different, not all of these relationships are even really close to linear, because there's some fairly complicated physics going on with the electrical potential in those junctions. So we need to really have a lot of information to sort out what the voltage means on a thermocouple. If we look at this table, this is a similar chart showing the voltage output, and it's only a relatively small millivolt level output for a wide variety of different combinations of thermocouple alloys. And one thing to notice is when we get over here to platinum and tungsten and rhodium and so on, these are pretty expensive metals. They're not as sensitive as thermocouples. However, big thing to notice, they allow you to make measurements out to really high temperatures. More common thermocouples would be made out of things like nickel and chrome, nickel and aluminum. The most common thermocouple in use is probably a type K thermocouple, and you'll be using one of these in the lab. Now, the thermocouple voltage that comes out of that type K thermocouple depends on the temperature, and it's referenced to 0 degrees Celsius. So, for example, if we're at a temperature below 0, we'll have a negative voltage in the table here, and the way to read this voltage is negative 150. That would be negative 149, negative 148, and so on. Or if we go over here to positive temperatures, if we had 310, we would expect to see a positive voltage of 12.624 millivolts relative to a 0 degrees Celsius junction. And if we had 313, then 310, 11, 12, 13, we'd have 12.78. So just a tiny bit more in millivolts, about 1/10 of a millivolt more. So this is the kind of tabulated data that you can find that'll tell you about the sensitivity of different thermocouples. You would probably never use this except in some test operations to get exact values here. More likely what you would do is you would use a polynomial fit. And Burns et al., all of these guys at the National Institute for Standards and Technology in April '93 put out a monograph with polynomial fits for the voltage that you'll get out of all of the different types of thermocouples. And this one, for example, is for a J-type thermocouple. Again, one of the fairly common types of thermocouples. So if you sum up over all of these constants and the temperature raised to each of these powers, 0, 1, 2, 3, so up to 8th order, then you would get a pretty good value for the voltage that you would measure. Now, all of that stuff is what makes thermocouples kind of hard to work with. Thermocouples have gotten an awful lot easier to work with in relatively recent years with the introduction of chips like this MAX31855. It has built-in cold junction compensation. It translates from your thermocouple voltage directly to a digital output and allows you to make readings for a whole variety of different types of thermocouples with high accuracy, better than a 1/4 degree Celsius resolution, which is better than the accuracy that you'd expect for most thermocouples, and doesn't require you to worry about cold junction compensation yourself. So if you take a thermocouple with about $1 or $2 worth of wire and add in one of these cold junction compensation circuits, you've got a highly rugged measurement device for low cost and low complexity, at least in terms of the complexity that you have to worry about in your application. So finally, what it comes down to is choosing temperature sensors. IC sensors are really cheap, easy to implement, not so rugged, and they have a really limited temperature range. So if you're measuring something around room temperature or not an awful lot warmer, these things are going to work just fine. Thermistors, also cheap, but they're non-linear. They have a large resistance change, so you can use them in just a voltage divider circuit, and they'll go to considerably higher temperatures than the IC sensors, up to 200 or 300 degrees Celsius. Platinum resistance temperature detectors or other similar devices, they're expensive, but if you need high accuracy and you're careful when you're measuring those small resistance changes, these are probably the best device for making high performance, very accurate temperature measurements. Usually in most practical products, you don't need that accuracy. You need low cost and ruggedness. If you can't stay down in the temperature range where these guys will work without breaking, then you really need to go with thermocouples. Thermocouples are an excellent solution. They do need cold junction compensation, but they can be very small, so they can go very fast, and you can go up to temperatures that you'll find in flames. So very often thermocouples are the preferred solution.